Welcome to lecture number 26 in our course on fundamentals of transport processes, where we had started deriving general conservation equations for mass and energy. I told you that we will defer discussion of the momentum conservation equation because momentum itself is a vector and it can diffuse in 3 different directions and it makes things complicated. So, first we considered a Cartesian coordinate system and we derived the mass conservation equation for this Cartesian coordinate system. So, the surfaces we consider a volume whose surfaces are bounded by surfaces of constant coordinate. So, in this particular cubic volume, the bottom and top surfaces are at constant values of z, the left and right surfaces are at constant values of y, the front and the back surfaces are at constant values of x. And we write a conservation equation which basically states that the change in mass within a time delta t is equal to what comes in minus what goes out plus any production of mass due to a reaction within this differential volume. So, this accumulation of mass within this differential volume in a time delta t, we wrote that as the concentration. Note that the center of this differential volume is at the location x, y and z. So, therefore, the accumulation of mass is equal to the concentration at x, y, z at time t plus delta t minus the concentration at x, y, z t, okay, multiplied by delta x, delta y, delta z. Okay. Note that when we take the accumulation term, t is changing between t and t plus delta t, but x, y and z are remaining a constant. That is, we are sitting at one particular location in space and finding out how the concentration changes in time. Okay. The flux is defined at bounding surfaces. The flux at the surface at z, we consider surfaces at z minus delta z by 2 and z plus delta z by 2. The flux at the surface z minus delta z by 2 is equal to the flux J z, because at the surface z minus delta z by 2, the flux is positive, it results in accumulation if material enters the differential volume. The flux J z is positive in the plus z direction. Okay. Therefore, a flux J z at the surface z minus delta z by 2 results in an accumulation within that volume. Flux J z at z plus delta z by 2 is leaving the differential volume. Therefore, that results in mass decreasing within this differential volume. Okay. Therefore, the mass in at z minus delta z by 2 is equal to J z times the area delta x delta y of this bottom surface times delta t. Similarly, the mass in at y minus delta y by 2 on the left face and x minus delta x by 2 on the rear face of this cubic volume. What about the mass out? At the surface at z plus delta z by 2, if there is a flux J z in the positive z direction, that results in mass leaving this differential volume. Therefore, that is the mass going out, resulting in a decrease in the mass within the volume. Therefore, the mass out at z plus delta z by 2 is equal to J z at z plus delta z by 2 times delta x, delta y, delta t. And similarly, at y plus delta y by 2 and x plus delta x by 2. In addition to that, there is also mass coming in and leaving because there is fluid flow. A fluid velocity carries mass with it, and therefore, if fluid comes into the differential volume, there is going to be a net mass coming into that differential volume. Okay. That is the convective transport. The fluxes that I have just calculated are the diffusive parts, they are due to diffusion. There is also a convective part due to the mean convection. And these the flux due to convection is the concentration times the velocity. Therefore, the total mass in is going to be concentration times velocity times the area and the time interval. And you have exactly analogous contributions due to convection. Surfaces at z minus delta z by 2, x minus delta x by 2 and y minus delta y by 2, there is mass coming in due to convection. And at the other surfaces at x plus delta x by 2, y plus delta y by 2 and z plus delta z by 2, there is mass leaving due to diffusion. In addition, there could be some production of mass that is going to be equal to S, which is the production per unit volume per unit time times delta t. For example, the production of mass due to a reaction dCA by dt is equal to minus kCA if it is first order. That production is the rate of increase of concentration with time, which means that the rate of production of mass per unit volume per unit time. Okay, so, that is the production term. Put all of these together and divide by volume and time in order to get what is called a difference equation. Okay. A difference equation, this entire equation here, okay, I have written it down in detail for you. This difference equation basically contains, first of all, a change in concentration between two time intervals at the same location, change in concentration between two time intervals at the same location. Okay. The difference in concentration times ux at x plus delta x by 2 minus, I am sorry, the difference in concentration times ux at x minus delta x by 2 minus x plus delta x by 2 divided by delta x. That is, when I take the concentration at x minus delta x by 2, that is the rear phase. At the rear phase, I am finding out the average concentration times the velocity. That is, I am taking it at the location y and z, because that is the center point of the rear phase, times x minus delta x by 2. So, in this difference term, the y and z coordinates are being kept a constant, only x is varying, okay, and so on with the other terms. Okay. So, and when you take the limit of delta x, delta y, delta z going to 0, you get a partial differential equation. Okay. I have written out that partial differential equation for you here. The partial derivative with respect to x implies that y, z and t are constant. Partial derivative with respect to y implies that x, z and t are constant, and the partial derivative with respect to z implies that x, y and t are constant. The partial time derivative implies that x, y and z are constant, same location. Okay. So, this is a partial differential equation. Okay. I showed you how to write that in a more compact form using vector notation. Okay. I defined the velocity vector. Velocity is of course a vector, it has 3 components and 3 unit vectors. Okay. The flux is also a vector. The flux in the x direction is equal to d times the derivative of x of concentration in the x direction. Okay. So, the Fick's law along the x direction. One can also have concentration variations in the y and z directions. Therefore, the flux is also a vector. Okay. It has contributions in the x, y and z directions. Okay. And the terms in the equation I showed you can be written as del dot cu, okay, where u is a vector, and minus del dot j, where j is a flux vector, okay, where the gradient operator is Ex times d by dx plus Ey d by dy plus Ez times d by dz. So, I can write it compactly in this form. Written in this form, the equation are actually independent of coordinate systems. One can find equivalent descriptions in both the cylindrical and spherical coordinate systems, in which these terms reduce to exactly the same form. Okay. So, one can find alternative descriptions in which these terms are written this way, they reduce exactly to the same form. We will look at that. We will look at how to get these derivations, so that we can get these terms into exactly this form. Okay. The components of the flux I wrote in terms of the variation of concentration with respect to the 3 coordinates using Fick's law of diffusion. Okay. And once you do that, you get an equation shown in red there, okay, which contains the Laplacian operator del square. The Laplacian operator del square is d square by dx square plus d square by dy square plus d square by dz square. Okay. So, it contains the Laplacian operator. Okay. And therefore, finally, I can write the concentration equation in this form in a Cartesian coordinate system. Okay. This is valid for any geometry in Cartesian coordinates, okay. And the energy conservation equation can be written in a similar form. Okay. The heat flux, okay, in Cartesian coordinates can be written as Q is equal to minus K grad T, analogous to J is equal to minus D grad C for the mass flux, where K is the thermal conductivity, Q is the energy flux, energy per unit area per unit time. Okay. And using that is Fourier's law for heat diffusion, using that I can get this temperature equation. Okay. I just substitute the temperature instead of concentration and the thermal diffusivity instead of the mass diffusivity. Okay. So, these are general equations, and we started applying them for a specific case of the conduction in a cubic volume. Okay. So, I have a cubic volume in which the front and back faces have 0 flux, the top and bottom faces are temperature T naught, the left face is at temperature T L, the right face is at temperature T R. Okay. Exactly at T is equal to 0, the cube was prepared in such a way that the temperature within the cube everywhere was equal to T naught. And at time T is equal to 0, I imposed a temperature T L at the left face, a temperature T R at the right face, and I want to find out how the temperature varies both with position and with time. Okay. I told you that since there is insulation in the front and the back, there is no temperature variation, okay, in the front and the back, and therefore, you would expect that there is no variation along the z coordinate, because a temperature that is independent of z will satisfy the equation. It will also satisfy the boundary condition, that is dt dz has to be equal to 0 at the front and the back. Note that this equation is a linear partial differential equation. For a linear equation, provided you have consistent boundary conditions, it is guaranteed that a solution exists and it is unique. So, if I can find a solution which satisfies the boundary conditions for this linear equation, then I know that that is the only solution. In this particular case, if I postulate that the temperature is independent of z, okay, that solution identically satisfies the flux conditions at the front and the back. Okay. Therefore, a temperature that is independent of z satisfies the differential equation, it satisfies the boundary conditions as well. Therefore, it is a valid solution, and since the equation is linear, I know that that is the only solution. Okay. So, when you have 0 flux conditions at the front and the back, you will find that there is no variation in that direction. So, this reduces to a 2-dimensional problem, okay, in the x and y coordinates and an unsteady problem in time. And we started looking at the procedure to solve this problem. First things first, we scaled the x and y coordinates by h, because that was the length scale. We defined a scale temperature T minus T naught by T naught, okay, and a scale time. And we got the differential equation, second order in x and y, first order in time. It requires 2 boundary conditions and 1 initial condition. The boundary conditions were T is equal to 0 at both the top and bottom faces, because T star is equal to T minus T naught by T naught. So, that has to be equal to 0 at the bottom and the top faces. On the left and the right faces, it is not 0. Okay, you have a non-zero temperature at both the left and the right faces. And at initial time, T star is equal to 0 everywhere. Okay. Throughout the domain, at the initial time, you have just applied the 2 temperatures on the left and the right. Initially, the temperature everywhere was equal to 0. So, this is the problem that we would like to solve. So, first things first, we need to find out what is the steady solution for the temperature field in this geometry, because in the long time limit, we would expect that the temperature converges to a final steady value, and It is that steady value that we should try to find out first. After that, we can go and find out what is the transient part, okay, the part at initial time, the difference between the actual temperature and the steady temperature is the transient part of the temperature. So, for the steady temperature, I set the time derivative equal to 0 and I just get a partial differential equation in x and y coordinates. The boundary conditions for the steady temperature profile are identical to the boundary conditions for the original temperature profile, because I am keeping the temperature a constant, okay, 0 on the top and bottom, TL on the left and TR on the right. Therefore, the temperature even in the final steady state has to have exactly the same boundary conditions. We started off doing separation of variables, okay. Ts is equal to a function of x times a function of y, substituted that into the equation, divided by x y, and we got an equation which contained two terms. One is only a function of x, the other is only a function of y. That means that each of these functions individually has to be a constant, okay. And the sum of these two constants has to be equal to 0 to satisfy this differential equation. Therefore, if 1 over x d square x by dx square is equal to c, then 1 over y times d square y by dy star square has to be equal to minus c. Should this constant be positive or negative? That is where we had left off in the last lecture. How does one decide whether this constant has to be positive or negative? If you recall, when we discussed separation of variables for the transient problem, in that case we had homogeneous boundary conditions in the two spatial directions, and there was an initial condition for the transient problem which was not homogeneous. There was a forcing at the initial time. Since the boundary conditions were homogeneous in the spatial coordinate, we took the constant to be negative for that spatial operator, okay. It's only if you take a negative constant that you get sine and cosine functions, and you can satisfy homogeneous boundary conditions on two surfaces. If you take the constant to be positive, then you get exponential solutions, and you cannot satisfy boundary conditions on the two surfaces, okay. So, therefore, we have to take the constant to be negative in the direction where the boundary condition is homogeneous. Coming back to the boundary conditions here, you can see that the boundary conditions are homogeneous in the y direction. T star is equal to 0 at y equal to 0 and T star is equal to 0 at y is equal to 1. This is the homogeneous direction. Therefore, you have to get sine and cosine solutions in this direction, and therefore, this constant c has to be a positive constant, so that you can get homogeneous boundary conditions in that direction. Okay. So, let us call this constant c as some beta n square. Okay. This constant c is equal to some beta n square, okay, some. Okay. And the solution of this is y is equal to a sine of beta n y star plus b cos of beta n y star. Okay. If beta n is if 1 over y d square y by dy star square is equal to minus beta n square, then this is the solution. I require that at y star is equal to 0, capital Y is equal to 0, which means that b has to be equal to 0. Okay. So, it is only a sine function, and at y star is equal to 1, capital Y is equal to 0. Okay. Capital Y will be 0 either if a is equal to 0 or if beta n is equal to n times pi. Okay. A cannot be 0, because if a is 0 and b is equal to 0, the solution is y is equal to 0 everywhere. So, therefore, a cannot be 0, therefore, beta n has got to be equal to n times y. Okay. So, therefore, the solution for y are of the form y n is equal to sin n pi y star, exactly the same that we got for the separation of variables for the unsteady unidirectional transport problem. That is because this solution is a property of this operator, okay, it is the property of this particular operator. Okay. So, this is the solution for y. Okay. What about the solution for x? Okay. In this case, d square x by d x square is equal to plus beta n square, okay, which means that capital X is equal to some constant c e power plus n pi x plus d e power minus n pi x, okay, where c and d are constants. Okay. And therefore, the steady solution T s star is equal to times sine of n pi y. So, any integer value of n satisfies the boundary conditions in the y direction. Okay. Any integer value of n satisfies the boundary conditions in the y direction. Okay. That means that the most general solution is the solution is a summation over all possible values of n. Okay, a summation over all possible values of n, where C n and d n are unknown coefficients. Okay. We have satisfied, we have enforced boundary conditions in the y direction, we have not yet enforced boundary conditions in the x direction. Okay. What are the boundary conditions in the x direction? Okay. The boundary conditions at x is equal to 0, t is equal to T L. At x is equal to 0, t is equal to T L. Okay. This implies that, I am sorry, T S. Okay. This implies that summation n is equal to 1 to infinity of C n plus T n sin n pi y The other boundary condition is that at x star is equal to L, T s which implies that the summation So, from these two boundary conditions, we have to evaluate the constants C n and D n. How do we do that? We use, as before, the orthogonality relations. Okay. As we have done earlier, we will use the orthogonality relations. Multiply both sides by sin m pi y star, okay, and integrate. Okay. Integrate from 0 to 1. Okay. If I do that, I will get summation n is equal to 1 to infinity C n plus d n times integral of sin n pi y times sin m pi y, okay, which is basically going to end up being delta m n by 2. Okay. This is equal to integral dy T L sin m pi y. Note that if I multiply by sin m pi y and integrate from 0 to 1, okay, on the left hand side from the orthogonality relation, I will get delta m n by 2. Okay. I can do that for the second equation, summation n is equal to 1 to infinity of C n e power n pi plus d n e power minus n pi into delta m n by 2 is equal to integral 0 to 1 times T r sin m pi y. Okay. Now, delta m n is 1 if m is equal to n and it is 0 otherwise. Okay. So, the summation n is equal to 1 to infinity of delta m n times C n plus d n is just going to be equal to half C m plus d m is equal to 2 by m pi times T L, okay, and half of C m e power m pi plus d m e power minus m pi is equal to 2 by m pi into T r. Okay. And these are two simultaneous equations which I can now solve in order to get the constants C n and d n. Okay. And the values of the constants C n and d n turn out to be equal to C m is equal to 4 by m pi T r minus e power minus m pi T L by 1 minus e power minus m pi and d m T L minus So, with these we get the final solution of the equation, the steady equation T s is equal to summation of n is equal to 1 to infinity of C n e power n pi x plus d n e power minus n pi x sin . So, crucial to the solution was actually identifying a region where a direction in which we have homogeneous boundary conditions. Okay. Once we identified a direction in which we have homogeneous boundary conditions, we know that the solution has to be sine and cosine functions in that particular direction. Okay. In the other direction, of course, it will be exponentials, exponentially increasing or decreasing. Okay. And the constants can be determined from the inhomogeneous terms. Okay, for the exponentially increasing and decreasing functions. So, that is the basic idea of how we extend a solution for separation of variables to 2 dimensions from 1 dimension. Okay. So far, we have got only the steady part of the solution. How about the unsteady part of the solution? Okay. So, for the unsteady part, we will be using separation of variables once again, okay, but in this particular case, whenever we do separation of variables, we have to ensure that there is only one inhomogeneous direction, that all other directions are homogeneous. Okay. If all other directions are homogeneous, then we will get eigenvalues and basis functions in all of those directions. There will be one inhomogeneous direction where the initial condition or the boundary condition will end up forcing the profile. Okay. So, the transient transient temperature was defined as the actual temperature minus the steady temperature. Okay. The actual temperature satisfied the equation this was the equation that was satisfied by the actual temperature. The steady temperature satisfied the equation d square T steady. Okay. So, you subtract the two and use the fact that the steady temperature has no time dependence, okay, and you will get the equation for the transient temperature. Okay. So, this is the equation for the transient temperature profile. Okay. How about the boundary conditions? And this is important. Okay. Boundary conditions. Okay. At T sorry. Y star is equal to 0, T star is equal to 0, and the steady temperature was also equal to 0, okay, which means that the transient temperature, the difference between these two is equal to 0. Okay. Y star is equal to 1, the temperature is once again equal to 0, the steady temperature is also equal to 0, which means that the transient temperature is equal to 0, the difference between these two. Okay. At x star is equal to 0, T star was equal to the temperature on the left. The steady temperature was also equal to the temperature on the left. Note that we applied the same boundary conditions for the steady part as for the total temperature field, which means that the transient temperature is equal to 0. Okay. Similarly, on the right side, and the steady part is also equal to the temperature on the right hand side, which implied that the transient part is equal to 0. So, for the transient part alone, in both the spatial coordinates, I am getting homogeneous boundary conditions. For both the spatial coordinates, you end up with homogeneous boundary conditions. What is not homogeneous is the initial condition. Okay. At T star is equal to 0, this, the temperature was equal to 0 initially, because the dimensional temperature T was equal to T naught. Okay. The steady temperature is independent of time. The steady temperature is independent of time. Therefore, the transient temperature is the difference between these two. This is going to be equal to minus Ts. Okay. So, the forcing is coming in at the initial time for this particular equation. So, separation of variables. T star transient is equal to some function of x, some function of y, some function of time. Okay, it is an additional function of time, which I will call as theta of t. Okay. Put that into the equation, simplify, divide throughout by x, y, theta, okay, and you end up with an equation of the form 1 over theta d theta by dt is equal to 1 over x d square x by dx square plus 1 by y d square y by dy square. So, I have an equation in which the left hand side is only a function of time, the right hand side contains two terms, one of which is only a function of x, the other is only a function of y. Okay. So, I have an equation where the left hand side is only a function of time, in the right hand side the first term is only a function of x and the second term is only a function of y. That means that each of these individually have to be constants. Okay. What should those constants be? Okay. Clearly, in both the x and y directions, I have homogeneous boundary conditions. T star for the transient part is identically equal to 0, left, right, top and bottom. Therefore, the constants for both of these directions have to be negative. Okay. So, the constants for both of these directions have to be negative. Okay. We also know what those constants should be. Okay. If the constant is negative, the solution is in the form of sine and cosine functions. Okay. Clearly, the cos function does not satisfy the condition that the temperature is 0 at x is equal to 0 or y is equal to 0. Okay. Therefore, the only solution is the sine function. In order to satisfy the boundary condition at x is equal to 1 and y is equal to 1, I have to have a sine of n pi times x star. Okay. So, therefore, the solutions that I get for x and y are of the form x n is equal to sine n pi x and y n is equal to sine. Note that the integers that I use for x and y could in general be different. Okay. So, I should have y m is equal to sine of m pi y. Okay. So, if x n is of the form sine of n pi x and y n is m is of the form sine of m pi y, okay, that means my solution for theta has to satisfy 1 over theta d theta by dt is equal to minus of n square plus m square times pi square. Okay. Which means that theta is equal to some constant. Okay. Let us call it as a e power minus n square plus m square pi square t star. Okay. So, that is the final solution for theta. So, therefore, finally, the transient part of the temperature is equal to theta times x times y, okay, which is equal to a e power minus n square plus m square pi square t star sine of n pi x sine of m pi y. Okay. So, this solution for any value of n and m satisfies the equation. That means that the most general solution is a summation over all values of n as well as over all values of m. Okay. So, the summation n is equal to 1 to infinity, summation m is equal to 1 to infinity of a n m. A n m is the coefficient, okay, and then I have an exponential term and two functions, one basis function for the x direction, another basis function for the y direction. Okay. So, I have two basis functions here, one along the x direction and the other along the y direction with two eigenvalues, n pi for the x direction and m pi for the y direction. How do I determine the constants? You determine that from the initial condition. you determine the constant from the initial condition, that is that at T star is equal to 0, the temperature is equal to minus the steady state temperature. Okay. It's equal to minus of the steady state temperature. Okay. Therefore, that means that summation n is equal to 1 to infinity, m is equal to 1 to infinity. Okay. At T star is equal to 0, the exponential is just 1. Okay. The exponential part is just 1. So, I just have a and m sin n pi x star sin m pi y star is equal to minus the steady state temperature. Note that the steady state temperature is a function of both x and y. Okay, the steady state temperature is a function of both x and y. Okay, I had got for you the solution for the steady state temperature earlier. Okay. So, this was the steady state temperature that we had got earlier. Okay. It is a function both of x and y. It has is a sine function in the y coordinate and it is exponential in the x direction. Okay. So, this is a function of both x, y. Okay. So, this is the equation I have to solve, and the way you solve that is to use orthogonality conditions simultaneously in both the x and the y directions. Okay. Use the orthogonality conditions simultaneously in both the x and y directions. That is, I multiply by sin p pi x times sin q pi y, where p and q are both integers. Okay, so, I multiply by one sine function in the x direction, one sine function in the y direction, and integrate over 0 less than x less than 1 and 0 less than y less than 1. That is, I multiply by sin p pi x, sin q pi y, integrate over both the x and the y coordinates from 0 to 1. Okay. Okay, if I do that on the left hand side, integral of sin n pi x times sin p pi x from x is equal to 0 to 1 will basically give me sin n pi x times sin p pi x from 0 to 1 will give me delta n p by 2, sin of m pi y times sin of q pi y will give me delta n q by 2. Okay. It's equal to minus integral dx integral dy ts of x and y sin p pi x sin q pi y. I have summation from n is equal to 1 to infinity of a n m times delta n p by 2. Okay. Summation m is equal to 1 to infinity of a n m times delta of m q by 2. M q by 2. Okay. So, this is just going to be equal to a p q by 4, okay, because delta n p is non-zero only when n is equal to p, and delta m q is non-zero only when m is equal to q. So, I just get a p q by 4 is equal to minus integral dx dy t s of x y sin p pi x sin of q pi y. okay, and both of these are from 0 to 1. And if I look at this integral 0 to 1 dx, integral 0 to 1 dy of sine of p pi x times sine q pi y times the temperature solution. If you recall, the temperature solution was summation n is equal to 1 to infinity of Cn e power n pi x plus dn e power minus n pi x sine n2 sine of n pi y. Okay. Now, sine n pi y times sine q pi y will be equal to delta n q by 2. Okay. So, this the product of these two, this one times this one integrated over this is just the old orthogonality relation that I had. Okay. So, this is just going to be equal to integral 0 to 1 dx sine p pi x, okay, into Cn e power n pi x plus dn e power minus n pi x, okay, into delta n q by 2. Okay. So, this is just going to be equal to integral 0 to 1 dx sine p pi x into C q e power q pi x plus d q e power minus q pi x whole divided by 2. So, I just need to carry out this integration in order to evaluate the actual value of the constants. Okay. So, this a p q is equal to minus of this. Okay. So, using this I can evaluate the value of each constant in that series. Okay. Okay. And once I have evaluated these constants, I now have the solution for the transient part of the temperature profile. Okay. So, this is the solution for the transient part of the temperature profile, in which I have evaluated the constants using similarities using separation of variables. I have the steady temperature profile as well, and in that case as well I have evaluated constants using separation of variables, and therefore, I have an analytical solution for the entire temperature profile. Okay. So, this is how one solves separation of variables problems involving more than one spatial coordinate as well as unsteady separation of variables. First things first, we have to find out what is the steady solution. Okay. That is important because we have to recover the steady solution in the limit as time goes to infinity. That means that I have to separate out the temperature into a steady and a transient part. That transient part has to decrease to 0 in the long time limit, so that I recover that steady solution in the long time limit. So, first I have to find a steady solution. That steady solution is obtained by solving a second order differential equation in two coordinates. Okay. In this particular case, we had homogeneous boundary conditions in one coordinate, that is in the y direction. We had homogeneous boundary conditions for the steady problem, and therefore, we got an eigenvalue problem in that y direction, in which the eigenvalues were n pi, the basis functions were sine of n pi y. Okay. There was an inhomogeneous direction, the x direction, where the temperature on the left face was not 0, the temperature on the right face was not 0 either. For that transient solution for that inhomogeneous direction, we managed to obtain a solution basically in the form of exponentials, one exponentially decreasing, the other exponentially increasing. And the final solution was a series expansion with the basis functions in the y direction as well as the exponentially increasing and decreasing functions in the x direction. And then I showed you how to use similarity variables, how to use the orthogonality relation in order to obtain the value of that solution in that direction. Okay. So, we used orthogonality relations for the steady problem in order to obtain the values of each of these constants. Okay. We use orthogonality relations in order to obtain the value for each of these constants. Okay. Basically, you have to solve a simultaneous equation in two variables in order to determine the values of these constants. So, that was for the steady part in the limit of t going to infinity. And then we went on to the transient part of the solution. You subtract the steady part from the total solution in order to get the transient part. Okay. Because the steady solution as well as the total solution have exactly the same boundary conditions, the transient part has homogeneous boundary conditions in all directions, in all spatial directions. There is an inhomogeneous boundary condition only at initial time t is equal to 0. This is important. When we solve a separation of variables problem, we have to make sure that there is homogeneous boundary conditions in all directions except one. That is the inhomogeneous direction where we will find what the solution is. And that was done by a two-step procedure here. The initial problem that we had homogeneous boundary condition in the y direction, inhomogeneous in x and inhomogeneous in time. We first separated that into a steady problem where we had one homogeneous and one inhomogeneous direction, and a transient problem which was homogeneous in all directions, but inhomogeneous in the initial condition at time t is equal to 0. For the transient problem, because we had homogeneous boundary conditions in all spatial directions, we were able to get eigenvalue problems in both those directions, sign functions in both those directions. The time the solution for the function of time turned out to be exponential in that case, and exponentially decreasing function in the time coordinate. Okay. And putting all of those together, we were able to obtain a solution, and we simultaneously used orthogonality in both the x and y coordinates in order to find out what is the value of that solution. Okay. So, here we simultaneously used orthogonality in both the x and the y coordinates in order to find out those coefficients in that equation, and that completes the final solution. So, just to recap, whenever we use separation of variables in multiple directions, we have to make sure that it is steady, that it is homogeneous in all directions except one. That one direction is the forcing direction, and we will get eigenvalue solutions for all directions except one, and that solution for that direction which is not homogeneous is calculated using the orthogonality relations for the basis functions. When we do not have homogeneous boundary conditions in multiple directions, we have to reduce the problem to a sequence of problems, each of which has inhomogeneous boundary conditions in only one direction and homogeneous in all other directions. Okay. And how do you reduce it to that sequence of problems? I showed you a first example here, how one reduces it to a sequence of problems in this particular case. We will see later on that one can reduce it to a sequence of problems in other cases as well. Okay. As we proceed, we will get more experience in how to reduce it to a sequence of problems. Okay. So, this was derivation of the conservation equation for mass and energy in the Cartesian coordinate system, and how does one solve problems using that in the Cartesian coordinate system. Next time, we will derive exactly the same thing for a spherical coordinate system. Okay. And I will show you how it is done for a spherical coordinate system. I do not want to do it in detail for a cylindrical coordinate system because it is just a tedious exercise. I will leave it to you to do it for a cylindrical coordinate system. I will just give you the final result. Okay. For the spherical coordinate system, in the next lecture, I will show you how to derive exactly the same conservation equation. And after that, we will look at situations where diffusion is dominant and situations where convection is dominant. How does one solve equations for each of these cases? Okay. So, next class we will start obtaining a differential equation, balance equation for a spherical coordinate system, and then I will show you how to use that in order to solve problems. So, we will see you in the next lecture. Thank you.